Okay, guys, let me just finish up the purple handout. Okay, the diazonium chemistry. We can react an aniline with nitrous acid and make a diazonium. What is a diazonium? Diazonium is two nitrogens, okay? Two, di. Aza is nitrogen, okay? This is a diazonium. And the nitrogen bonded to the ring, or the R group, which is usually an aromatic ring, is positive. And thus we have a minus. Diazonium is made reacting aniline with nitrous acid. Not nitric acid, nitrous acid. HNO2, not 3. Nitrous. Okay? Nitrous acid, though, is not stable. Not a stable acid like nitric acid is. Nitrous acid is made by reacting NO2 minus with what? What do you need?
Water.
Not water.
Sodium.
H plus. You need an H plus source to protonate the nitrite. What is this? Nitrite. Okay, nitrite, not nitrate. Nitrous, not nitric. Okay, and this is going to be like sodium nitrite. Okay. So sodium nitrite and then a proton source, strong acid, HCl, sulfuric acid, okay, some strong acid. This generates HNO2 in situ. Okay, it's generated in the reaction, in the flask. It's stable enough to be generated, but it's not stable enough to be like stored in the stockroom. It just won't last. Okay. But these are, your nitrite salts are very stable. So you just supply the proton, then you get nitrous acid. So that's what this is generating. And the aniline reacts with nitrous acid to give the diazonium. Let's look at that mechanism. HNO2. That's nitrous acid right there, yeah? One lone pair, yeah? On nitrogen. We want to make one lone pair. All right, that's not anything there. One lone pair. Remember when we did nitric acid? We protonated it, we lost water, we made what? Then the ring reacted with, we make nitro groups. Nitronium ion, yes. That's the NO2 plus. This is called a nitroso ion. NO plus. That's what we want to get. How do we get there from here? What do we need to lose?
An OH?
OH. How do you make oxygen of our leaving group?
Protonated.
Protonated. Okay? You need to protonate this. I'm not going to redraw it. I'm just going to draw it. Can I draw it protonated? Okay? That is, the acid actually protonates the nitrite twice. It protonates it once to go neutral, nitrous acid. Then it protonates it again to get to this point. And now these electrons can move in here and kick this off. And what does that lead to?
Nitroso ion?
Yes, that gives you your nitroso ion. Yeah, there is one lone pair there, yes, good. Then the aniline, the amine, will react with this. These electrons bond to the nitrogen and move these electrons back, because we do have dipole here. And that would give R, I'm just going to say R for the benzene ring. Does that arrow movement give that over there? Yeah?
Yes.
It's good? At this point, we can do H plus transfer. From here, what do we need to lose to get to our diazonium?
The water? Oh, no, sorry, just the two H's. The two H's that are bonded to the...
water.
Yeah, and what else do we need to lose?
Oh, and the water, sorry. And the oxygen.
Well, oxygen is part of water. Yeah, essentially this thing needs to lose two H's and an O, and it ultimately will be water. But I was getting at we need to lose the oxygen. If we do proton transfer to this oxygen, we just took the proton off of the nitrogen and put it on the oxygen. Proton transfer. We've done that before, right? Now we can actually do resonance structure. These electrons we can move in here and these out here. Double bond to N, single bond to O, H. Now the plus charge is on this nitrogen here. Now we can do proton transfer again. We now have an acidic proton. Instead of it sitting on the nitrogen, we can move it to the oxygen. H plus transfer again. Double bond to N, single bond to O. Now we have lone pair back, yeah? Now what do we need to do to get to the final? One more step and we have our diazonium.
Water.
Anytime we can make a pi bond and kick off a leaving group, that's easy to do. What does that arrow movement do?
The triple bond between the nitrogen and the water leaves.
Right, there's your diazonium. Okay, you draw your arrow to your diazonium. And yes, we said we were going to make water. Well, there we did. That last step, we made the water. Fascinating reaction. This is Mother Nature. This reaction occurs. Very common reaction with anilines. Reaction with nitrous acid, get a diazonium. All right? Now the diazonium is typically not isolated. You don't make these and say, hey, here's my diazonium. Look, no. They tend to be explosive. This thing wants to lose nitrogen into gas. So this is in solution. And often brackets like this means it's not isolated, right? We've seen that before. Maybe didn't mention that or focus on it, but it's not isolated. It's in the reaction, this is an intermediate. Okay? But that N2 is a good leaving group. And nitrogen would love to get some electrons back. Now, the mechanism from this point is not SN2, SN1, but we can do substitution and replace the nitrogen, the N2, with other things. And we can give lots of other things, very versatile. The mechanisms are probably radical. We're not looking at this. Okay, what can you do? You can replace the diazonium with halogens. Let's first start here. Chlorine and bromine, you have copper 1 chloride or copper 1 bromide. With those, you cannot use just like sodium chloride or sodium bromide. You have to have a copper. And the copper is necessary because it's probably a radical reaction, and the copper helps the radical. Okay? You cannot just use sodium chloride. Now, when you use the copper, that's often called Sandmeyer reaction. But in general, all this is sometimes called Sandmeyer reactions. So it talks to Sandmeyer, okay? So either Sandmeyer or diazonium. I usually just say diazonium reactions. But Sandmeyer is the name of these. In particular, copper. Okay? And so we can basically replace all this. Under my hands, the N2, now it's bromine or something. So that would be like bromobenzene you can make here. It's another way to get a bromine on the ring. Or any halogen. Instead of brominating it by EAS, we're replacing the aniline with essentially a bromine. Iodine. With iodine, you can use just simple iodide salts like sodium and potassium iodide. You don't need the copper. And actually, copper kind of hurts the reaction with iodine. The reason you don't need it is because I- can actually do redox chemistry pretty easily, where BrCl- can't. All right? So you can just use Ki, and the iodine will replace that. By the way, what else do you get here? Whenever you get this, it's not shown here, is it? But plus what? Any of these reactions plus nitrogen gas. Okay? That's the fate of the N2, right? Just nitrogen gas. Right? Everybody take a deep breath. Yeah? You just inhaled a lot of nitrogen gas. This is produced in the reaction, and you often see bubbles. Anybody see bubbles and frothing yesterday as the reaction took place? This was nitrogen gas being released. Okay? All these are going to produce nitrogen gas. And we're doing the Ki. And you're also making water, right? This is synthesis of water. We showed that over there, right? You often synthesize water. And then the potassium is going to sit with probably like potassium chloride. There is an anion here that the potassium can sit with. Or what other anion you got here. If we use sulfuric acid, this is going to be like sulfate anion here. Okay? Okay. Fluorine. If you remember, it's very hard to put a fluorine on a ring by an EAS because fluorine is so reactive. And remember, we said diazonium. Go back to that handout. Well, here's the diazonium. But it's a little bit unique. You don't just use copper fluoride or sodium fluoride, potassium fluoride. What you can do here is react your diazonium with tetrafluoroboric acid, which we've never seen before. And what will happen is you'll get an anion exchange. Whatever anion you got here will exchange, and you'll get a BF4- anion. All right, often see boron. This is boron with 3 F's. And what's the charge of the boron? 1, 2, 3, 4. Minus. That's the anion. But often salts that have this anion often are insoluble in water. So what happens is when you add that, this actually precipitates. Okay? That salt will precipitate. And you actually filter it and you get it. Diazonium. But remember I said you usually don't isolate these, mainly because they're explosive? Well, you got to be careful. It can be explosive. So you don't want to do this on too large a scale. You want to have a blast shield, etc. Okay? Because that solid could just go off and release all that nitrogen. But if you heat this in a controlled manner and explode it, but controlled, you will get a reaction. You'll actually get the fluorine bonding to the ring, plus nitrogen gas coming out, plus what? If we just balance that out, BF3. And this is a way to get like fluorobenzene. Where again, trying to fluorinate benzene using fluorine is very difficult. It's much more common to make fluorobenzene from actually what? From aniline. Replace the amino with fluorine. Okay? Everybody with me? Questions? Some of you look like you have questions. Good? Okay, other reactions. Let's skip that one here. Copper cyanide, very similar to copper chloride and copper bromide. You can replace the diazonium with cyano group or nitron group. Let's look at this one now. If you just take your diazonium and heat it with aqueous acid, you can get a phenol OH on the ring. And that's basically the OH replacing the diazonium. Now this may be a ionic mechanism. That may be, we can certainly show this mechanism, whether it's correct or not, but there's some evidence that it may be. For example, this nitrogen is a decent leaving group, positive nitrogen. This thing can just leave. If that left, what would that give? What would be here now?
A carbocation.
Yes, plus what?
N2.
Plus that nitrogen gas. This thing will just leave, and you'll go from one molecule to two. That's driven by entropy. This will happen with heat. Now, this is not a good cation. And I've actually told you to never do this, or that's worse than a primary carbocation. That's a cation that was originally coming from an sp2 carbon. Not a great cation. All right? But then water could just come in here and react to this, and what would that do? That would give that, right? Well, that could just lose proton and go neutral, and then there you go. There's your phenol. Okay? Now, usually you don't want this to happen because you want to do some other chemistry. So if you don't want this to happen, instead of heating, you would do what? If heat causes something that you don't want, what would you do instead of heating it?
Chill it?
You would
Chill it?
you would chill it, or you certainly would not heat. But what's the opposite of heating?
Chilling.
Keep it cold. That'll keep this from happening if you don't want this to happen. Okay? So when you make the diazonium, usually you do it cold. Because this thing, with a little heat, if it gets a little warming, maybe from exothermic reaction that's going on, it's just going to decompose and you're going to end up with maybe a phenol. Where you want this to last long enough so you can add in these other reagents and get the chemistry you want, which again is probably radical reactions and it's hard to show mechanism. This one indeed may be an ionic mechanism. So we can make phenols this way, which if you remember or think about it, we did not make any other way. And so this is the only way that we will see to make a phenol. Last reaction. What are we replacing the nitrogen here in this reaction with?
Hydrogen?
Just an H. Well, this is C6H5 and something else, right? The something else here is an H. You can do this with this guy. What's the name of that? H3PO2. A little bit of Gen Chem nomenclature here, right? Nitrite, nitrate, nitrous, nitric. What is that one there? What is phosphoric acid, which is most common? H3PO4. What is H3PO3 then? Phosphorus acid.
Hypofluorescent.
What is H3PO2?
Hypofluorescent.
Hypophosphorus acid. Yes, hypophosphorus acid. Nobody calls it that. It's got a common name, phosphinic acid. Okay, that's a common name. Phosphinic acid. Phosphinic acid is known to be a reducing acid. Since it's reducing, what does it supply? Not electrons, but in terms of, if something gets reduced in organic chemistry, we add what?
Hydrogen?
Or an H.
H's. Yes. We're reducing, we're adding an H. Okay? And phosphinic acid will add H's in a reduction. Okay? Because if you think about it, you don't need H plus. If you go this route, what do we need to react this way to get an H here? H plus, you'll have no electrons. You need 2 electrons to make a bond. You need H minus.
Yeah.
Okay? That's a reduction. Okay? So, we have a way to make benzene. Because that's just benzene. Here's how you make it. You take benzene and you nitrate it. Then you reduce the nitro group to the amine. Then you convert it to the diazonium. Then you come in here with phosphoric acid and you make benzene. Question?
So pretty much you could cycle all of these?
I'm kind of joking here. The idea is you start with benzene, you do all this, and you end up with benzene. Yeah, we cycled through. Here's the take home. Nobody's making benzene this way. You can just buy benzene. And you can get it from petroleum. All right? So when would you ever want to do this reaction? There are times when you would want to remove this group. But you're not doing it with aniline. It's probably more of a sophisticated molecule that maybe has an amine there for some reason. But essentially what we're doing here with that reaction is you can remove this and go back to just nothing there, H there, by that route. Okay? These are diazonium reactions. Again, mechanism is not really here. But it's great reaction for your toolbox, synthesis. Okay? Very versatile, lots of things. And there's lots of things that are not here. For example, you can also make SH compounds. There's many products here that aren't shown here. And actually, in graduate school, I was trying to make an SH compound, right? Convert this to the SH by the Diazonium process, okay? And one of the sort of the scariest times I've ever been in lab. And so I was making it, actually had a first year student with me. We were kind of doing it together, and I was more advanced. We were doing it on a pretty large scale. The flask was about the size of a volleyball. Okay, flask about this big. All right. We made the Diazonium, and then we started dripping in this other reagent that's not shown to make this. As soon as we started dripping it in from a funnel, it was dripping in. Bam! You ever heard a go-kart backfire or a lawnmower backfire?
Yeah.
That's what it sounded like. I mean, not quite, but okay. All right. So I sort of ran that way. And I told him, I said, stop the funnel. And around the corner, I heard it go bam again. And we just sort of stopped. We just added water and kind of diluted it out. And then later on, I read that this can be replaced. Basically, I read later on, it said diazonium sulfides are particularly unstable and explosive. I'm like, okay, I believe it. The only problem is I should have sort of known that before I did the reaction. Yeah? And then maybe I wouldn't have been doing it on the volleyball scale. I might have been doing it on a smaller scale. So instead of going bam, it might have just burped or something. All right? And we could have. All right. So we never completed that and sort of abandoned ship on that. But, you know, whatever you're making of this nitrogen coming out, if it comes out too fast and just goes exothermic, creating that gas. Explosions is where you create these gases and they come out so quick. Okay? All right, that's diazonium chemistry. Take a look. There's an example procedure on the flip side here. Actually doing the amine to iodide. Okay? MultiStep synthesis. Back over here. How can we make this from benzene? Anybody have a synthesis? Let's go backwards here. Let's see. Let's go back to carboxylic acid. Let's take one group off. Let's go backwards. Eventually get to benzene where we have taken both groups off. Is this reasonable? Could we come back here? If we had benzoic acid, could you nitrate it and get that?
No.
No, why not?
It's a messenger.
Yes. Not going to work. It's a meta director. So we cannot go back. We cannot propose just having benzoic acid and nitrating. No good. Can we go back the other way? Can we take nitrobenzene and put on a carboxylic acid?
No.
Not directly.
Good. We actually have two problems here. First off, we know no way to put on a carboxylic directly. We can do indirectly. But what's the other problem here?
Nitrate.
It's also a meta-director. So any reaction we do, whether it's direct or indirect, we have the wrong director here. Because the new group needs to go para. Both of these are meta-directors. So can we even make this compound?
Yes.
What we have to recognize here is, and this is often in these syntheses, what you have to recognize is there's often a precursor group that has different directing What's a precursor to a nitro? Nothing. We do directly nitrate. Nope. Is there a precursor to this?
An alkyl.
Yeah.
Alkane.
No, yeah.
Alkyl. Okay? This can keep going back to maybe a methyl. Now it's actually best here to do ethyl. And either way we have issues because you're probably going to see methyl used, but ethyl for synthesis reasons. We go back to that because if we had this, could we make this?
Yes.
What would you react that with?
Potassium permanganate.
KMNO4 would give us that. But this is a precursor, and what type of director is this?
OrthoPara.
OrthoPara, which we need to get the nitropara. Now we sort of see how we can do this. If we have this, what would you do with this first?
You
Nitrate it.
You want to nitrate first. Nitrate while it's still an OrthoPara director. HNO 2 or 3?
3.
3. We use nitrous acid for diazonium. We use nitric acid for nitration. Right? You can use H plus catalyst. Is that absolutely required? Did you use H plus? Did you use sulfuric acid when you nitrated chlorine? No, you did not. What is that going to give?
The nitro group here.
Now it will also give ortho. It may give some ortho nitro. That's okay. In your synthesis, we can say we're just going to purify this and we're going to get our para. So we don't even have to worry about that. Yes, it's there, but we're going to purify and get this. Now what do we want to do with this?
You can react it to make a carboxylic acid group.
Okay. We really don't want to do this here. That would work, but then that turns it into a meta director. We want to nitrate first. Now that we have this, what do we do to get the final?
We do the KMNO.
Yeah.
Now we do KMNO4. So we got to start with benzene. How would you make this from benzene?
Friedel-Crafts.
Yeah, Friedel Crafts.
What would you use?
An ethyl like halide.
I'm going to do this. We want to do two-step route. Acylation, followed by what?
Reducing. Yeah.
Friedel-Crafts acylation, followed by Clemmensen reduction to give the alkyl group, which is an OrthoPara director. We can then nitrate. Nitro would go para. And then we can oxidize our alkyl group to the carboxylic acid with loss of CO2. Questions about that one? Looks good?
Couldn't you just add an ethyl group directly without having to do a Friedel-Crafts? Like I started off with something that was an alkene and then I reacted it with HF to add, just because I didn't even.
Well, it's always best to do acylation followed by reduction.
Okay.
Because what's the problem with putting alkyl group on directly? Polyalkylation.
Okay.
You can directly do it. I'd rather you propose a two-step, because usually you want to have a high-yielding multi-step synthesis. And the two-step is going to be a higher yielding. Okay. It's important to know that the two-step is better. The direct alkylation had problems, polyalkylation. Okay. Okay, there's some over on the flip side for you to work. We also need to look at, well, there are some for you to work here. I mean, look here. Both of these are OrthoPara Directors. You put one on, the next one then is going to want to go ortho or para. How do you get this meta relationship? You need a meta director at some point. Is there a precursor that is a meta director?
Yes.
You can easily do what
That's
we
very
just did.
similar to the one we just did. Okay? But then, look here, both are OrthoPara Directors. Is there a precursor that is a meta director?
That one.
Yeah, the
Do we have a precursor to this? No. Do we have a precursor to that? What is it?
nitro, NO2.
Nitro group, which is a meta director. So you want to do a reaction when it's in the nitro stage, then convert nitro to amino. Try some of these, including, down here, 3 groups on the ring. This one over here is kind of interesting. How about this one? Try that one too.
Try nitro and do a bunch
Try
of-
them all. Try nitrobenzene.
Yeah.
Explosive. That's more explosive than trinitrotoluene because it has more nitrogen content. With toluene, you got an extra carbon that actually stabilizes this some. You take the methyl off of TNT, it's even more explosive. But on paper, it works.
Try nitro.
Things are safer on paper. But there may be another way. Think about that. Okay, we need to look at another thing with the diazonium. Diazonium again. There's another reaction we can do with diazonium. What is HONO?
That's your nitrous acid. Nitrous acid.
Yeah, it's HNO2, right? It's HNO2. But sometimes you may see it written as HONO. That way you can just say HONO. Okay? It's HNO2. Now we know that's not stable, but it's produced and we can still show that. If you're making amine aniline with nitrous acid, what do you get? Diazonium. Another reaction of diazoniums, other than replacing the nitrogen, is you can actually do a reaction where it remains there. And you can actually do an EAS. If you bring in another ring with an electron donating group, usually, you can get what's called a diazo-coupling reaction. And these two sort of react together. Because this nitrogen ultimately wants its lone pair back. It can get its lone pair back by taking these 2 electrons, sort of here, then this bond is broken. But we can also get it back by something coming in here and moving these this way. And that's what happens here. And this is basically an EAS. What type of director do we have here?
Group 1.
Group 1.
OrthoPara. Basically, these electrons can attack here, and just like an EAS, and move those there. And this electron movement would give, I'm just going to call this phenyl. Double bond here. This arrow gives the lone pair back, right? There was a lone pair there all together. It's still there. But now this is bonded to the ring, pair position at the OH. And I use that double bond, so we've got that one and that one remaining. Windshield wiper over. That becomes positive. There's an H here. This is just EAS again, okay? And then we can just restore the aromaticity. Something takes this H. There's got to be a minus here. Whatever this minus is, take the H. These electrons move in. And that should give this product shown, right? OH. We put the double bond back in, and we made HX. The X took the H to restore the aromatic. It's just an EAS where some other aromatic ring is attacking here this nitrogen, and so the nitrogen is still in there. You don't lose nitrogen gas. Very common reaction. They're so common because these products are dyes, tend to be dyes, very heavily colored, like red and orange, etc. Why are they dyes? We'll go back to UV vids. What's going to make something absorb? To be highly colored, it means it absorbs in the visible. What's going to make something absorb into the visible from
Being highly conjugated.
highly conjugated? Very good. And you see how highly conjugated it is? Pi system. There's two p orbitals here, pi bond. All this is conjugated, including with this lone pair here. Starting here, it's conjugation all the way through there, and it leads to it being absorbing into the visible very intensely. And these are often dyes. They're called azo dyes. Now, this reaction could have gone ortho. Okay? All right? Plus ortho. It's always a possibility. This is an OrthoPara Director. There's some examples of these below. Typically, this is from the Diazonium and electron-rich, or I already called that electron donating group, electron-rich aromatic. Those react the best, and others just don't react as well. Typically, anytime you see an azo dye, one of the rings is going to have an activating group, a donating group. And when you see that, that was the ring that reacted, as opposed to this. This was already there from the Diazonium. The other ring came in here. And if we look at examples, first off, names of some of these, that got hole punch. Sorry, you can look up acetal. Diazonium. Does one of these rings contain an activating group or donating group? Yeah, that one. And so that's the bond you made. That ring reacted with just regular Diazonium here. What's the name of that one? Solvent yellow 124. Technically yellow. That compound is used to dye diesel fuel in Europe to make it yellow. That way you can easily tell the difference between diesel and regular gasoline. Well, sometimes people may want to say, hey, you want some of my diesel? I don't know that's diesel, that might be gas. Well, the law says it has to be colored yellow, so, okay, they put this dye in it. Sunset yellow, okay? Does one of these rings have an activating group?
The OH.
You see, And it went ortho to that group to get this. It could have went over there. Maybe you get some over there too, and you have to separate. But, okay. That's also got some other groups. This is sunset yellow. This is putting food, including Doritos. Okay. Makes your Doritos yellow-orange. Nice, tasty. Of course, diazoniums are also known to cause cancer. These dyes are cancer-causing, typically. So enjoy your Doritos. There's one down here below that's red. It's called FD&C, red number 4. Good. This is in maraschino cherries, makes them red. Because otherwise they tend to be sort of pink. And people don't like pink cherries, they want red cherries. And so we put some red dye in it, make them good. Right? So you have this in here, it's red. Does one of these rings have a strong donating group?
OH.
You see? So that bond is probably what's made ortho to the OH, it reacted. Okay? Now there's actually a good compound here, a drug. The first antibiotic drug was Prontosil. It was an azo dye. And a guy named Paul Ehrlich was using this dye to stain, for biological staining. But he observed that the stain was killing the microbes. Acting as an antibiotic. That compound there was actually given, I think there's a handout in here, read it, given to the grandchild of FDR. Because he had an infection. Back then, this was before penicillin. It turns out, by the way, does one of these rings have a strong activating group?
Yeah, the animal.
See, it has 2. Ortho to there, make that ring. It turns out that this was not actually the active component. The microbes or something was reducing this. This can be reduced. That can be cleaved in the body, and this becomes NH2. And the other one becomes NH2. But what did I circle there? Have you ever seen that compound before? No. Have you ever used that compound before? Yes, everybody halogenated that compound. What did I circle? Sulfanilamide. This compound was being cleaved to generate sulfanilamide, and that was the actual drug. Eventually they figured that out, and they stopped giving that, and instead they just started giving sulfanilamide. So that's the active component. So Prontosil was actually a prodrug. It wasn't the active drug, but it was the thing that turned into the drug through a reduction. That was better anyway, because Prontosil causes cancer. You don't want too much of it. Of course, it kills the microbes. Would you rather have cancer and kill microbes, or just kill microbes? Just kill microbes. So let's just give sulfanilamide. Okay, try to rush through that, guys. We're about out of time. Questions? We have one more handout for the exam, too. We'll be hitting that on Monday. Yes.